Remember that we skipped the last three assumptions in the previous class, and we went on to introduce your take-home finals. So I'll just come back to this slide and finish off those last three assumptions which we left off. So up to plane stress state, we have already done everything. So the next one that we would like to have is what is known as the Kirchhoff-Love assumption. And this is essentially assuming that the in-plane strains are linear through the thickness. So in other words, if you see this laminate that we have over here, and if you introduce this coordinate x3 along the thickness, that's essentially what we are saying through the thickness coordinate is x3. And by in-plane strains, recollect that we mean the gamma alpha betas, where alpha and beta take on the values 1 and 2, right? So there are two normal strains along x1 and along x2. So uh, it's gamma 1 along x1, that is the extension or contraction. And then the gamma 2, which is also an extension or contraction, depending on the sign, positive or negative, respectively, along the x2 direction. So that's what we retain apart from the shear strain within the plane, which is the gamma 1, 2, which is happening entirely in the mid plane or any reference surface that you choose for this laminate. So what we are saying here is that gamma alpha beta is linear in X3, means that we can rewrite gamma alpha beta, which is a function of, remember, X1, X2, X3, and in general time as well, is equal to a constant with respect to x3, which we will call as epsilon alpha beta, a function of x1 and x2 only in terms of space. It could be a function of time in a dynamics problem. And then you have a linear term, which is x3 times rho alpha beta, which is also a function just like epsilon alpha beta of only the in-plane coordinates x1, x2, apart from the time in a dynamics problem, right? So now remember that this is called as the 3D strain, the capital gammas or the uppercase gamma that we have. The reason, as we said, it's called 3D is because it involves all the three spatial dimensions, right? So similarly, the nomenclature for your epsilons and rhos is that they are 2D strains in the sense that they depend only on x1 and x2. As you see over here, epsilon depends only on two spatial dimensions. Rho also depends only on two spatial dimensions. And therefore, we call these as 2D strains. Now, you see, just like the seventh assumption, we have put the eighth assumption also in red. So what that essentially means is that it's a dicey assumption. It's something that can be quite dangerous. We saw the dangers of plane stress in terms of its inability to deal with delaminations, compatibility, boundary conditions. We also forgot to mention that it can violate even the equilibrium equations. And in fact, some people some researchers use that as a blessing in disguise to get back the through the thickness stresses which we left out, namely sigma I3, using the equilibrium equations which are violated. Because you start off assuming sigma I3 equal to 0, but if you use the 3D equilibrium equations, you can actually get sigma I3, which is non-zero. And so some people use this whole methodology to make a wrong assumption and then go back and get what is right. So it's an indirect way of doing things, not a very wise approach to take, but it's essentially a saving grace. Okay, so now coming back to the eighth assumption of Kirchhoff-Love, These are two great mathematicians, which we have had in the recent history a few centuries ago. And both of them have done an enormous amount of work. There are many different fields. And so this is one of their major contributions where they have introduced a simplification in the model, which actually, if you go back to our questions that we've been asking about necessity and relevance, that is over here, necessary or relevant, uh, the thing is it's not relevant because in reality the through the thickness linearity of the in-plane strains is not something which holds. But if you're looking at very thin structures, that is a first reasonably good first cut approximation. But we can get to that approximation even without making this assumption. So remember that whether it's the strains, the stresses, displacements, these are all unknown quantities. When you're given a particular structure and you know the load on that, you want to determine what are the stress distributions, what are the strain distributions, all the measure numbers that is, and then the three displacement measure numbers. You want to get it in all the directions. But what happens in the case of making an assumption like this is you're forcing the model to have a certain behavior, which may or may not be true for that particular model. And as you go for thicker and thicker laminates, and many of the uh, monocoque constructions will fall in that category. And even semi-monocoque, if you do not have enough number of stringers, spars, etc., then the through the thickness stresses become very large. Plane stress itself is violated, and the linearity of the gamma alpha beta, which is an independent assumption, is also violated, and therefore you end up with fairly erroneous solutions based on erroneous models. But to the credit of Kirchhoff-Love, their solution happens to be an asymptotically correct solution in the sense that if we were not to make this assumption and try to derive the so-called zeroth order approximation or what is the leading terms, then we will see that this is all that happens. This is in fact a solution that comes up for especially for thin laminates or any thin shells for that matter, as long as the initial curvature is fairly small. This is again similar to in the beam problem, what we call as the Euler-Bernoulli beam theory. So let me just go to my whiteboard over here. I think it should be visible, right? Yeah. Can you see my whiteboard? Yeah. Okay. Thanks. So now if you look at this thing, we have, remember, 1D structures and 2D structures, which we in general called as beams. That's our terminology for it, but it actually includes rods, columns, frames, shafts, etc. Okay, in other words, there can be torsion, there can be compression, there can be bending, there can be extension, whatever it is, as long as one of the dimensions is large compared to the other two dimensions, namely L is very large compared to B and H, we call it one-dimensional structure. And here in this case, it's exactly the opposite. We're calling it L and B uh, very large compared to H. Okay, so here, of course, we call it as shells, but of course, it includes plates because plates are nothing but zero curvature shells, and it also includes membranes because they have zero stiffness plates or shells, right? So zero stiffness in the flexural sense, that is the bending stiffness goes to zero. So does the torsional stiffness as well. Or an equivalent of that in the 1D would be like a cord, okay, so or a wire. So essentially something which is very, very easy to flex, right? And unlike this, which has a reasonable rigidity in the bending, a cord or a wire essentially has zero stiffness. So also something which is very famous in physics is a string. We call the string theory, which is essentially a fallout of this same geometry, but goes on to cover other aspects of physics as well. Now, so this is the two main classifications, which we also answered as to why, in terms of the geometry, why these kinds of beams and shells are important in flying vehicle structures. From that point of view, we understand, but now in the form of an analysis, we want to know how to model these once we have this kind of a simplification from the geometry in terms of the orders of magnitude of the different variables that are involved. So coming back to the assumption that we just invoked, that is the from your deformable bodies course, you will be aware of the simple engineering beam theory, where we have something very, very similar, again, two great mathematicians and physicists. Though it may or may not have been introduced in with this particular terminology. So essentially, it's what we call as the simple engineering beam theory, where you try to find out the let's say the bending moment diagrams, the shear force diagrams, etc., and you related the bending moment to the other things like stresses and the displacements, etc. Right now, the same thing we are doing by using the Kirchhoff-Love hypothesis over here. So what we were talking about in terms of the smaller dimensions here, so remember, is the cross section. Whereas here, the smaller dimension that we are talking about is h, which is the thickness So equivalent of the cross section that we saw over here is the thickness line element. So whatever approximations were made in the simple engineering beam theory are made in what is known as the classical plate theory. And when initial curvature is there, it's a shell theory. And when we use composites, we bring in another adjective here to say laminated, like the laminates that we saw at the bottom of this particular picture. That's something which can be included in this model as well. Okay, so this is the title given to the 1D theory, the simplest 1D theory that you can have. In the name itself, you have simple engineering beam theory, and the simplest theory you can have for plates or shells for that matter is the classical laminated plate or shell theory, which we abbreviate as CLPT or CLST, depending upon whether it does not have initial curvature or has initial curvature before the application of the loads. Once the loads are applied, if there are bending loads, obviously you will induce curvatures. So that's part of CLPT as well. Now, in order to understand this Kirchhoff-Love hypothesis, which we introduced as a gamma alpha beta equal to epsilon alpha beta plus x3 rho alpha beta, what we are actually doing in terms of the physicality, because this is mathematics, but in physicality, what we are essentially saying is that we are introducing a new variable, which is the in case you have introduced x3 coordinate is such that at the mid surface or mid plane of the laminate, it is x3 equal to 0. So then it becomes the strains at that location, because if in this equation, gamma alpha beta equal to epsilon alpha beta plus x3 rho alpha beta, if I set x3 equal to 0, I would get gamma alpha beta equal to epsilon alpha beta. So in other words, gamma alpha beta at x3 equal to 0 is epsilon alpha beta. So in other words, you can use this equation to define epsilon alpha beta, that is the so-called mid-plane strains. I can define as the 3D strains, which I already know is a green Lagrange strain, whose definitions I already know, at x3 equal to 0. Okay, so this is an important result that you ought to remember. And similarly, if you look at the first derivative of that equation with respect to x3, then you can see that I can define my rho alpha beta as gamma alpha beta comma 3, by which I mean dou by dou x3, right? So it's a shorthand notation for derivatives. Partial derivative with respect to x3 is referred to as comma 3, but not, so this is, wherever I take, it doesn't matter. So this is, remember that, because once I take the derivative of this equation that I have over here, equation 1, if I call it, then you see that um, the first term vanishes because it's independent of x3. It's constant with respect to x3. And the second one is linear in x3, and therefore what all that you're left with is rho alpha beta. So in other words, the same equation, which is your Kirchhoff-Love hypothesis, I can rewrite as gamma alpha beta is equal to, what we are saying is that it is a gamma alpha beta at x3 equal to 0 plus a gamma alpha beta comma 3 at x3 equal to 0 multiplied by x3. Okay, so that's essentially what we are saying. So it's like, if you look at it actually closely, it's nothing but a Taylor series that you're familiar with, a power series, just that in reality it should have many more terms, higher order derivatives with respect to x3 and powers of x3, x3 squared, x3 cube, and so on. All that we are saying, all that Kirchhoff and Love said is that these are all approximately 0. So in other words, they neglected the product of the higher order derivatives of gamma alpha beta with respect to x3 multiplied by the higher powers of x3. And that made a little bit of sense, because you remember that x3 is of the order of the height of the laminate or the thickness, which is very small compared to the order of the length and the breadth. So therefore, higher powers of x3 became smaller and smaller, and therefore you're dropping off those terms. That is the whole idea behind this assumption. So remember that even though we're calling it mid-plane over here, a more appropriate name for this instead of mid-plane would be a reference surface strain. Why? Because I as the modeler have the liberty to introduce my reference surface wherever I want. It need not be necessarily at, oops, So I need not necessarily put it at the mid surface over here. In this case, there are four plies or four layers of different angles. So you see that the way I've drawn it with X3 starting from the mid surface, that is above the second layer and just before the third layer started. So that becomes the mid surface, assuming that all four layers are of the same thickness. Okay, which may or may not be the case. Sometimes different layers may be of different thicknesses. We have seen examples of hybrid composites where CFRP and GFRP are both used simultaneously, and you could have each of them of different thicknesses because based on their own manufacturing processes, slightly different thicknesses. But from other points of view, sometimes it might be more advisable to take a different reference surface because, for example, the aerodynamicist is the one from whom we get the major loads, and they will be talking about the loads at the aerodynamic center. And so that might not necessarily be at the center of this. It might be at the center of somewhere on the chord of the airfoil, whereas this is a skin panel, which is at a slightly higher height compared to. So what we are dealing with over here is, let's say, a wing. So the panel that we are talking about is a skin panel on the top, which is what we have drawn over here, right? Now that, whereas the aerodynamicist might be giving you the loads at quarter chord, for example, for subsonic aircraft, where they might define the lift, the drag, the pitching moment, etc. So we know it at some other location which is much below here. So you could have, for example, x3 equal to 0 starting from here, where there is not even any material as far as this particular panel is concerned. Doesn't matter. Okay, it's just a mathematical way of defining it. So your x3 will start at some positive value, and then it will go on to that positive value plus h, which is the total thickness of this um, laminate. So that freedom we have depending upon the particular problem, the kind of inputs we have, the kind of outputs we are looking at. So based on all of that, we might make a decision on what is an appropriate X3 datum to choose. Where do we start at X3 equal to 0? So that is why I mentioned over here that instead of calling it mid-plane, so we said that though many a times that nomenclature might be used, and many a times the datum might be chosen at the middle of the thickness of the laminate. It's not necessary. Sometimes it's more convenient and more useful to actually choose the reference surface somewhere else. So in general, we can call it as the reference surface strain. And still, this whole thing holds good that you're talking about the reference surfaces strain. So this becomes the reference surface strain. This becomes the reference surfaces curvature. Okay, remember each of these have three quantities. Here we call this as epsilon alpha beta. So we have epsilon 1, epsilon 2, and 2 epsilon 1, 2. Similarly, there we have rho 1, rho 2, and 2 rho 1, 2. Okay. Now these are Okay, it's not necessary to call this as in plane. So essentially, these are the reference surface normal streams. While this is the reference surface shear stream. So it's within the surface that we are essentially talking about. So it's in surface, right? On the other hand, these two are the reference surface bending curvatures. While this is the reference surfaces torsional curvature. So in other words, you're having something that you're trying to bend. So different layers will have different bending curvatures. So if I'm trying to bend this upwards, if this is a part of an aircraft wing, we know that the lift distribution is such that this will anyway bend upwards. So if it's bending upwards, you see that the top layers have lesser curvature compared to the bottom layers. In other words, the radius of curvature is more for the bottom, but the curvature itself is lower for the bottom layers because the curvature is defined as 1 divided by the radius of curvature. So you see that different locations of X3 will have different curvatures, but there is the datum that we have chosen, which could be in many cases the mid plane or mid surface, but could be anything else as well. So that reference surface, whatever it is, whether it is within the actual material or outside, either on either side. So that particular reference surface is uh, thickness is its normal strains, its shear strains within the plane, and also the bending curvatures. Rho 11, rho 22 is because of the drag distribution, and similarly, because of the pitching moment that we showed, there is a twisting that is happening, and that twisting curvature is also there, right? So that which is what we call as rho 12 over here. So are there any questions or doubts so far on what we have introduced? You're good to go. Just show me a thumbs up. Yeah. Yeah. Okay. Right. So with that, we come to this, but I also wanted to showcase, in order for you to better understand what you already know from the simple engineering beam theory that was introduced to you in the deformable bodies course, where we make certain assumptions about the cross section. So remember, we said that here the cross section is the equivalent of the thickness line element. So whatever assumptions we are making about the cross section there is what we are making about the thickness line element over here. So you might recollect that two of the simplest, most important assumptions in this simple engineering beam theory, which is also called as the Euler-Bernoulli beam theory, is that first thing that you assume is that plane sections remain plane. In other words, we're saying that if this is a beam, I don't care whether it is extending, it is bending or twisting or combination of all of these. I know that there is a particular cross section or any arbitrary location along the length of the beam, along which I've introduced the coordinate system x1. So at some value of x1, let's say x1 star, I choose a particular cross section. Now, when the beam undergoes a deformation, there is something called the beam reference curve, which is the location of x2 and x3 equal to 0, which is what we have chosen, where the origin of the coordinate system is there and along the x1 axis. So that particular x1 axis undergoes a deformation and it reaches some other position, which we call as the deformed reference curve. We start with an undeformed reference curve and we go to a deformed reference curve. Now, what happens is that that particular cross section at x1 star also goes along with that reference curve, and it essentially reaches a particular location. So just let me sketch that to make it much more clearer. So we have some arbitrary cross section. This is a beam, therefore its length is large compared to the cross-sectional dimensions. Now we have introduced a coordinate system of x2, x3 along the cross-section and x1 along the length of the beam, right? Now, so if I draw the cross-section at some location x1 equal to some reference x1 star, then you have the coordinates x2 and x3 along that. So this is the point that I'm talking about. The loci of such points at different cross sections is what becomes your, if you join all of them, that becomes the what we call as undeformed beam reference curve. Okay. Now you apply a load. Let us say I fix this. Let's say it's part of the wing. So I fix one end, let's call it the fuselage, and the other end is free. And now we have a lift distribution, because of which the reference curve will now bend upwards like this. So you see that it bends upwards like that, right? Now, every cross section also goes along with that. So that particular cross section that we had over here at x1 equal to x1 star will also go along with that reference curve. And what Euler-Bernoulli are saying that because initially it was perpendicular to the reference curve, after deformation also it will remain perpendicular to the reference curve. Okay, so it moves along. So this particular cross section moves along because the beam is bending. And so therefore it goes along with the cross section, but it rotates only as much as the reference curve itself rotates at that point. So since they are initially at 90 degrees and both of them are rotating by the same amount, they maintain that orthogonality between them, maintain the 90 degrees between them. So which is what is expressed in this first uh, assumption where we say that the plane section remains plane. Okay. So then there is the second assumption. Oh, yeah. Before we go to that, there is an equivalent assumption that we see over here in this, which is contained within this, which we are saying that that particular line element that is there for a plate. Now, if you take a, instead of a beam, you take a plate. Now, in this plate, here, what was the smaller dimension for us was the cross section. Okay, whose that dimension, let's say in this case, it's a circular cross section. So its the diameter is very small compared to the length. On the other hand, when coming to the plate, we are saying that the thickness is very small compared to the length and the breadth. So the smaller dimension element that we're taking is no longer the cross section as in the beam, but now it is a line element. So somewhere at some, see here we took at some arbitrary value of x1 star, we took a cross section. Here we take at some arbitrary location of x1 star and x2 star at some location along the mid surface or any reference surface, we take the line element x3 varying from minus h by 2 to plus h by 2 if it's a mid plane, or some other value to some other value which is same value plus h, which is the total height of that plane. So whatever we are saying about the cross section in this case, we say about the normal line element in this case, because that was the equivalency that we marked out here, remember? So we said whatever we make assumptions about the cross sections for the 1D problem, we make the same kind of assumptions for the thickness or line element as far as the 2D problem, which is a plate or shell, is concerned. So here what we said is that plane section remains plane. What we are saying is that in this case we are taking that line element and saying that that's a line element, whatever we had, remains straight and remains of the same size. Here also, in fact, it's not explicitly mentioned in a lot of textbooks, but the plane section not only remains plane, but which means, of course, that its shape has not changed, but also its size doesn't change. The cross section is not actually allowed to deform within the plane as well, which means that actually something that we know for sure happens in the reality, which is the Poisson's effect, is also not accounted for when we say the plane section remains not only plane but of the same size. Okay, so it's very important that in this case, the thickness element is assumed to remain straight because it was initially straight, it remains straight, and it remains of the same size, which means that once again, the Poisson's effect is not accounted for in this particular model. Okay, so that is the equivalent in the plate theory. When we talk, instead of plane section remains plane, the straight element, which is the thickness element, remains straight and of the same size. Now we go back to the beam problem. There's a second assumption that you made in the simple engineering beam theory in deformable bodies, and that says that the plane section remains normal So we know that the way the cross section was chosen was it is perpendicular to the beam reference curve. Now we are saying that first of all it remains plane, but it also rotates in such a way, as I already mentioned, that both of them rotating by the same amount, which means that the orthogonality between the cross section and the reference curve remains, whether it is undeformed or deformed. Okay, irrespective of the load, as long as you're within a certain limit in terms of all the other assumptions that we have already made. So in terms of the coming back to the plate now, what is the equivalent of that? Now we are saying that there is this line element in the undeformed plate. The reference surface and the line element were perpendicular to each other. Now, when you bring in the deformation because of the loads, this is going to have a certain curvature. So the line element is also going to get a joyride on that reference surface, but it's such a way that it remains perpendicular to that curved surface. So that's essentially what we're looking. So if you were to just sketch that, what it looks like is that if the original plate that was there has gone on to become a surface like this. So that's essentially because of the loads that are applied. Then if you take any at some x1 star comma x2 star on this reference surface, there you had a line element like this, which is going, let's say if you choose the mid plane, then it's going from x3 equal to minus h by 2 to plus h by 2. Now what we are saying is that once, so here it was perpendicular to that reference surface. Now, after the deformation has taken place, it remains perpendicular to that reference surface. Okay, so wherever that particular location was. So this is similar to what we were saying about what I marked in blue in the case of the beam. The same thing we are talking about here. There we are talking of a reference cross-section remaining perpendicular to the reference curve. Here we are talking of the reference normal line element or the thickness line element remaining perpendicular to the reference surface. So you see the analogy in terms of the beam and the shell problem with respect to the each other. Then if you understand one, it's much easier to understand the other, because the logic or the whatever is the reasoning that is there in going from one step to another remains the same. It's just that you are talking of two different dimensions, because in this, remember, this 1D, how did we get to? Both cases, of course, we started off with a 3D problem. So here we broke the 3D into a 1D reference curve plus a 2D cross section. And therefore we ended up with the Euler-Bernoulli beam theory. On the other hand, here what we are doing is we are doing just the reverse. We are starting with a 2D, which we call as the reference surface, and then we have a 1D, which is the thickness line element, right? So in other words, so the analogy is between this smaller guy over here and the smaller guy over here. These two are analogous to each other. Okay, so whatever assumptions we made in the beam theory about the cross section, we make the same kind of assumptions about the thickness line element in the plate or shell theory. And what we end up is, of course, a theory for the 1D reference curve in this case and a 2D reference surface in this case, and which is why we call that as a 1D structure over here, and we call this as a 2D structure over here, is because we are left with the larger dimensions. The larger dimension in the case of the beam is the length. The larger dimension in the case of a plate is the length and the breadth. So both continue to remain in the problem. But a structure like this, if is a geometry like this, we have a three levels of orders of magnitude. The thickness is small compared to the breadth, and the breadth is small compared to the length. So a structure like this, exact similar kind of a geometry, can be modeled not only as 3D and 2D, but also as 1D. So all three models are possible for this. Whereas for something like this, where there is no small dimension with respect to the cross section, here you can model it only as a 1D or a 3D, but we can't model it as a 2D, because the 2D model requires that there is one more small parameter associated with the cross section. There's no small parameter associated with the cross section in this case. Whereas the typical kind of beams that you use in a lot of aerospace applications, like we saw the I section, Z section, channel section, hat section, etc., all of those have a smaller dimension within the cross section, which is the thickness of each laminate or each wall. It could be closed also. It could be a box beam, like we have indicated before, or it could be a circular tube, circular shaft, which is thin walled, hollow circular shaft. So then when you have something like that, you again have a smaller dimension associated with the cross section, which is the thickness divided by the diameter, or thickness divided by the dimensions of the cross section. If it is square, the length, the width, or the height. So keep this in mind, that those are interfaces between 2D and 1D, because you can model both as 3D, 2D as well as 1D, many of the aerospace structures that are available. So it's a question of how much of accuracy you want, how much of efficiency you want. If you want a lot of efficiency, and if it is feasible for that particular model to go to 1D, you might as well go to 1D. There will be a small loss in accuracy, but if you do it properly, that will be negligible and not something to be worried about. On the other hand, if you are really concerned more about the accuracy, then you do a 2D model, which is a shell model for a structure like this, which is amenable to both. Or if you're even more concerned about the accuracy, then you do what is known as a 3D model, which many of the commercial software using finite element analysis are really good at, but just that they take a whole lot of time as the complexity of the structure becomes more and more from the material point of view, or the geometry point of view. Is this particular assumption clear? The so-called Kirchhoff-Love, what we did with respect to gamma, alpha, beta, breaking it into epsilons and rhos, both of which are now functions of lesser number of independent variables, because x3 is dropped out, comes out explicitly in this particular equation that I've shown over here. So this particular equation is what I'm talking about, which is the main thing that came out of the eighth assumption that we have made, which is essentially the assumption about the 3D strain being linear in the thickness. And also the analogy with the beams. If you have any questions, I'll be happy to answer it. Okay, so let's go ahead. This one go. Okay, but because I kept it, so I'll have to do that slide. So anyway, coming to the ninth assumption, which a lot of people do again, which is again in the danger zone, which is why I put it in the red font, is that people make assumptions about the displacement and or stress field. Most cases, they make assumptions about the displacement field rather than the stress field. But some people who understand the issues associated with displacement field assumption say that they don't make displacement field, but if you look closely, they are making an assumption either about the strain or the display or the stress, which is anyway equally dangerous. Just that they have shifted the danger from one part of the model to another part of the problem. In either case, it's an issue because remember, whether it's the displacement, whether it's the strain, whether it's the stress, all of these are unknown quantities, and it's very dangerous to assume about something that is unknown. Whether it's in life or in structural analysis, if you just blindly assume whatever you don't know, then you're in for some unpleasant surprises as well. Okay. It just so happened that some of these ended up as pleasant surprises, and so people continue to do that, but it's not necessarily a right thing to do. So just to give you an example of what this might entail in the displacement field assumption for a plate, let's go back to this. So what we assume over here is that, see, a plate or surface like this will have three measure numbers for the displacement field, which we know in general are functions of all the three spatial coordinates and time, right? The same thing in this case as well. Okay. So now what people do is they assume some of these as either constant with respect to x3. In other words, it doesn't depend on x3 and or linear in x3. Which, as you say, which, as you see, is actually equivalent of what is being done over here, because the strain is a derivative of the displacement field. Here, Kirchhoff and Love assumed that the strain is linear in x3. So if you assume that the displacement field, how it behaves with respect to x3, the derivatives of u are what we get as gamma. Remember, for example, if you want gamma 1, 1, we know that its linear part is just u1 comma 1, right? So if you have made an assumption about u1, it will translate to an assumption about gamma 1, 1. Same thing is the case with the other other two mid-surface or reference surface strains, which is u2 comma 2, u1 comma 2 plus u2 comma 1. And of course, there are the other three, which are the transverse strains. And because of the plane stress assumption, they're all functions of so what happens is this particular thing over here, this displacement field, whether you assume constant, linear, quadratic, whatever, different theories assume different things, that is going to lead to some assumptions about the uh, mid-plane or in-plane or reference surface strains, right? Now, that is in turn going to impact your gamma I3 as well, the transverse strains, both shear and transverse normal, which is gamma 33, right? So now all of these are going to get affected by an assumption about the displacement field, and sometimes some of these assumptions are even contradictory in some of the works, which is very, very sad state of affairs, especially for researchers. But as I said, what people do is sometimes they do not make this assumption, they let go of this uh, as if it's a great thing that they have done, but instead start making assumptions with respect to your sigma I3 and sigma alpha beta, one of which we already saw is that sigma I3 equal to 0, which is again that plane stress assumption over here, right? So they, in addition, they will make certain things about sigma alpha beta um, wrongly assumed. Here also, I should say wrongly, okay? Wrongly either assumed to be either constant. So here also it's wrongly, the sigma alpha beta is wrongly assumed constant, linear, quadratic, etc. People may have made a whole life out of this by publishing paper for each assumptions that they got cubic, quartic, etc. And this is of course again with respect to the thickness coordinate x3, because we're dealing with the plate or shell in which that is the only small dimension. If it's a beam, you have a similar kind of models that people are talking about, which is in terms of x2 and x3. So powers of x2 and x3 is what you expanded. And so at the end of the day, you get what are known as higher order shear deformation theories. There's a whole bunch of these different authors have come up with many, many different kinds of higher order shear deformation theories just by going on this power series, quartz constant, linear, quadratic, cubic, quartic, etc. And all of these higher order shear deformation theories, right from the first order shear deformation theory itself, you will see that there are problems that ensue out of this whole thing, and which is why they introduce what is known as, in the last assumption that we will see over here, empirical correction factors. Okay, this is the 10th and the last assumption that we have on the slide about how we go about modeling flight vehicle structures, whether made out of metals and or composites. So the 10th assumption is about empirical correction factors. Why do we need them? Because we made wrong assumptions. So when we make wrong assumptions, we end up with wrong results. We do an experiment to compare, and we are not able to validate with that. So you call it a validation when you're comparing your theoretical results or computational results with experimental results, then you call it as a validation. So usually you'll see that these two will have a huge difference. The difference between them, of course, is the error. Of course, there is a possibility, a remote possibility, that there were some experiments with the conduct of the experiment itself. Therefore, you don't know which is the appropriate benchmark to take. But more often than not, if there is some repeatability with the experimentation, the experiment is much more reliable, and therefore the theory or computational results that you get will have to match with that as closely as possible. If the error is fairly small, then it is acceptable. But if the error is large, then people end up with these so-called empirical, as I mentioned, Timoshenko beam theory is an example of that. So Here I was talking about, remember, on the left-hand side, I was talking about beams and about shells on this side. So the higher order shear deformation theories, which you can abbreviate as HOSDT, are there both for shells as well as beams. And the first of amongst them is called as the Timoshenko beam theory here. And in the case of the shell or the plate, you call it as the, based on the people who first came up with it, Reissner and Mindlin. Okay, so both of these will have those, even for the simplest geometry, if you take even, let's say, a square cross section, you will not get exact results from the Timoshenko beam theory. So you will introduce certain correction factors, which is essentially like curve fitting. You're saying that this is what I get from the experiment, some input variable to the output variable. The input variable could be some load that you have, let's say the bending moment or whatever, and the output could be a particular stress or a displacement or whatever. There'll be some curve that you get from the experiment, and you get something else from the theory. Okay, sometimes you might not have either all conservative or non-conservative also. Some places it might go above the experiment. So this is, let's say, you get the theoretical result and you have an experimental result, then obviously the validation fails. Okay, so then when you have the validation failing like that, you tend to bring in a correction factor and try to fit your theory so that it goes closer to the experiment. So that's essentially what your correction factors do, because they're empirical in nature. So you'll define it in a certain way for a square cross section. You'll define it in a certain different way if it's a rectangular cross section, certain different way if it's a circular cross section, and if it's an airfoil cross section, then it really God only save you, because it's going to be very, very complicated to determine those shear correction factors in the first place. So these theories become pretty much useless in such situations. Same thing in the case of the plate or shell theory. The first order shear deformation theory is called as Reissner-Mindlin plate or shell theory. It's very important for you to be aware of these things, but because these are kind of regularly used in a lot of publications, both textbooks as well as research papers, and even sometimes in the industry, just to get some rough cut approximations, it's fine as long as they use it only for that purpose. But if they go beyond that and try to employ these, then it's quite disastrous. So you have to be really aware of these things. So there's no point in trying to go through the details of these theories and trying to understand all their solution processes, etc., knowing fully well right up front that it's an erroneous assumption that we have started with, and therefore we end up with erroneous results. So we might as well not necessarily in a class like this where um, we have a shortage of time in terms of the number of things to be covered. There's no point in going to details about things that we know are anyway erroneous. So with this, we come to the end of all the assumptions over there. So if you have any questions, I'd be happy to answer with respect to any of these 10 assumptions that we have made. Okay, good to go. So let's, oops. Okay, so this is something that we rushed through. Just let me revise that. Yeah, so we started off. So this is what is directly going to be your take-home final as well, where we talked about different variables which describe the state of the mechanical loading. Then, oops, I'm going backwards. So then we said that we could do some bucketing into four categories or sets, which we called as loads, stresses, strains, and the deformations. And then we said, therefore, some of those might be given to us, some of them might not be. I'm not always looking at your video, so in case you have a question, doubt, just unmute yourself and let me know, because I may not be looking at your video in case you raise your hands or whatever. Okay. So now we said that some of these might be known, some of these might be unknown. So we need a set of equations to do relate all of these things and determine the unknowns in terms of the knowns. So those three sets of equations we uh, bucketed once again into three categories. Those three categories were equilibrium, the constitutive, and the kinematic categories. And then we said those three sets of equations depend on entirely different things. The equilibrium, for example, are just natural laws, whereas if you're looking at the constitutive law, it's entirely about materials. If you're looking at the kinematics, it's more all about geometry. So this is what we summarized at the end of last Thursday's class. So I'll just bring in all the lines over here in the animation. And we said that this is something that whatever the issues are with respect to composites can be resolved. And we have already done that in whatever we have introduced on that assumption slide. We've introduced direction dependent moduli, like examples of which were like ET, EL, new LT, and then we had GTT prime, etc. Right? So these are the things that we had in order to make sure that you're not talking of a single Young's modulus or a single Poisson's ratio, etc. So, or single shear modulus for that matter, GLT should also be there. So these are the five that are typically used. On the other hand, here we said that we introduce volume averaged stresses and strains. So in other words, you integrate sigma ij dv, so it's a volume integral, and divide it by the total volume. And that volume that we are talking of there is a what we call as a RVE, the representative volume element, which includes a sufficient number of fibers and sufficient amount of matrix in the same proportion that is there on an average within the entire material. And once we do that, we are able to replace the stresses with respect to this, because we are now dealing with hypothetical material, essentially an imaginary fictitious material that you have, which we call as the composite, and its properties we are associating with the overall behavior of the structure rather than of individual fibers and the matrix. In order to be able to do that, we do this not only for sigma, but the same thing we end up doing for um, the strains gamma as well. Okay, and of course we take the sigmas as well as gammas both into account, and eventually those averaged out sigmas and gammas is what we are relating by those constitutive laws that we have introduced. And the final form of that constitutive law, whatever we introduced, remember, is a 2D constitutive law because of the plane stress approximation, where we just said that we are relating our, let's say, gamma 1, 1, gamma 2, 2, and 2 gamma 1, 2 uh, in the in the principal material directions, which means that we are talking about one as L, the longitudinal direction, and two as the transverse or direction perpendicular to the fiber. So when we have something like that, we saw that these were zeros, and we ended up with 1 by EL, 1 by ET, 1 by GLT, and here we have mu, because this is the input is 1, so mu LT divided by EL, and mu TL divided by ET. And these are, of course, equal to each other because it's a symmetric matrix. So the 1, 2, and the 2, 1 terms. So both of them are not independent, which is why we have only 5 independent entities to deal with as far as a 2D composite is concerned. In other words, you have made a plane stress approximation. So once we know this, of course, we already know that because these three gammas are known, we can get the gamma I3 as a function of these gamma alpha betas, and from which we know all the gammas, and the displacement fields are defined in terms of that. So we can go about trying to determine that as well. Okay, so we know the compatibility has to be satisfied, because of which the six cannot be given independently, but because we have made the plane stress assumption, that will be violated. And that is one of the issues that is there with this whole methodology. Now, coming back to the bucketing problem, let's get to the examples from things that you already are aware of. We'll start with the simplest of the examples, what is known as the axial bar or the column. So instead of getting this notes, let me just start afresh with something over here. So remember that we are talking of loads, stresses, strains, and the deformations. Okay. Now we take a very, very simple example where we are going to be talking of just a rod. So if I cut this rod somewhere, I'm going to get some arbitrary cross section over here. Let's say that cross section is having an area A. Let's say it's having a length L. Okay. So now I can think of it as having an axial force F. And since I'm going to introduce a coordinate system x1 along that, I will call that as F1, because F is also a force, is also a vector. So it has measure numbers F1, F2, F3 parallel to the x1, x2, x3 axis. But in this case, simple example, we are considering only F1 to be non-zero, the other two to be 0, F2 and F3. So when we do that, of course, for it to be in equilibrium, I have to apply an F1 over here. Or equivalently, what I can do is, instead of putting an F1 over there, I can just fix that end. So the support will be offering that reaction that we just showed. So if we draw a free body diagram, it would look like what I just erased, right? So that's what you're talking about. So you have a certain F1 that is applied. So in this case, very easily we can see, we can go back to our load, stress, strain, and deformation. So we see that it is this F1 that is the load that you're applying here, which will come over here. So that's what we are talking of about in terms of the classification. In this simple problem, there are no other loads. This is the only load that is there. Now, what do you think would be the major stress coming out of this force F1? Because remember, there are many stress measure numbers, sigma 1, 1, 2, 2, 1, 2, etc. So which sigma would you expect here?
One. 1. 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1,
That's right. Absolutely. So you would expect a sigma 1, 1 to come here because you are seeing that if I take a free body diagram where I have cut, I have an F1 over here. It has to be equilibrated by stresses acting on this. And that surface that you have over there is perpendicular to the x1 direction. And therefore, the first subscript is taken care of this because it's perpendicular to x1. The second subscript, of course, is the direction of the stress itself, which has to be in such a way that it's opposite to your f1. So it's also parallel to the x1 axis, and therefore that is 1. And that's why what you have is sigma 1, 1 over there. Okay. So what do you think will be the strain occurring because of this sigma 1, 1? What would be the strain, main strain occurring because of this sigma 1, 1?
Gamma 1, 1.
Absolutely, yeah. So that's the direct effect. Would it be just this, or would you have other strains as well? In reality,
you would have, you also have gamma 2, gamma 2, 1.
why would you have gamma 2, 1? It's a shear strain, right? Whenever the subscripts are different from each other, you would end up with shear strain, right? So I'm trying to pull this rod. I'm trying to pull it apart. So what's happening is that it's going to extend, which is the what you already mentioned, gamma 1, 1. But you're also saying that there will be a gamma 2, 1, which is essentially this thing getting distorted in its plane. So in other words, this moving this way, this fixed. So you're essentially saying that this cross section is also going to move this way. Why would there be a gamma 2, 1?
It would be 2, 2, because you're having the Poisson's ratio where as you're stretching it, you're causing another strain.
Absolutely, absolutely. Yeah. So gamma 2, 1 is possible, but it's only when you have composites of a particular layup. The couplings might be there because of which gamma 2, 1 might be there. But if you're looking at the specially orthotropic directions, that is the principal material directions parallel to the fiber and perpendicular to it, or even for that matter, metals, you would not have gamma 2, 1. But as Nafis pointed out, you would have gamma 2, 2. Okay. So you would have gamma 2, 2, and for the same reason, you would have a gamma 3, 3, which are all Poisson's effects. Okay. So right now, let's not bother about these indirect effects, the coupling effects. Let's focus on the main effect, which is gamma 1, 1. Okay. What about the deformation? So let me once again also draw the other coordinate measures, which is x2 and x3. So in general, you will have a u1 along x1, a displacement measure number u2 along x2, a displacement measure number u3 along x3, right? But in this case, what would be the predominant displacement that is there of any material point? Amongst u1, u2, u3.
Can you repeat the question?
Yeah, I'm asking, see, we are trying to fill up all these, right? So we already filled up for loads. We filled up for stresses. This is the third bucket, strains we already filled up. We want to next fill up the deformations, okay? Which would include displacements and rotations. So the displacements that are generic are what I showed over here. That is U1, U2, and U3 in along the X1, X2, and X3 directions in a general problem. But this particular problem where I'm applying only F1, and this is a rod like this, which is having a length which is much larger compared to the breadth and the height. So this specific problem, the simple problem that we have, I'm asking which amongst these U1, U2, or U3 would be present, which would be the dominant displacement measure number.
U1.
Yeah. So it's quite obvious, right? So it might seem silly what I'm asking you and trying to get information from you, but I'm trying to start with something that is quite obvious, that you're very familiar with, to show how more complicated things can also be thought of in the same logical reasoning approach, which is the purpose of this exercise. So just bear with me if things seem too trivial at this point. So you're right, Nafis, so that the main deformation that you're going to get is U1. But just like you had gamma 22 and gamma 33 as Poisson's effect over here, here also you can in general have a little bit of U2 and U3. Remember, here we are talking of all 3D displacements. That is, all these U1, U2, U3, all the UIs are functions of x1, x2, x3, and time in general, right? So even though on the reference curve, you might not have a U2 and U3, at other locations on the cross section, you will have a U2 and U3. For example, if I'm pulling this and this has a positive Poisson's ratio, it's going to have deformed shape, let's say something like this, which is essentially contracting in the other direction. If I pull it apart sufficiently and the Poisson's ratio is reasonably large, then you might end up with something like this. It might be a similar shape, but the size is reduced. That's essentially what your Poisson's effect does. So you can see that in general, there can be U2 and U3 as well, just like you had a gamma 22 and gamma 33, but those are secondary effects, which are essentially your Poisson's effects. If they will be there because Poisson, in most cases, nu is not equal to 0, the Poisson's ratio in that particular direction that we are interested in, namely nu LT, and therefore you would have non-zero values for this. But there are some special cases where nu is 0, and therefore in those cases it will not be present. Whatever it is, that's not something that we are focusing on over here. We want to look at the major effects. So let's stick on to just gamma 11 and U1 over there. And so we'll just have these four, right? So now it's very clear that we have identified. So the first step of the whole thing is to identify for a particular given problem, what are the unknowns and what are the knowns. In this case, I'm applying F1. So this is a, oops. Yeah, so I'm applying F1, which is the force over here. And therefore, that is the known quantity. Okay, so in other words, this is known. Whereas all of these other things that we have bucketed and listed under stress, strain, and deformation are unknown quantities, which we want to determine, right? So which is where we need to bring in the equations correlating these variables. So even without talking about it, you can probably tell me from obvious intuition or your prior experience with working on a problem like this, what is the relationship between F1 and sigma 11?
Sigma 11 times the area would be the force.
Very good. Yeah. So you're saying that F1 is equal to the area times sigma 11 because St. Venant's principle works. We are in an interior location, which is sufficiently far from either of the boundaries. And therefore, how I apply F1, I'm showing here as almost like a concentrated force, doesn't matter. Okay. If I take this boundary, for example, yes, there will be singularities occurring close to where the force is applied. But in reality, that's not how it's applied. It's also a distributed force, but distributed probably over a smaller area. But doesn't matter, however it is applied, when you go to an interior, it is a uniform distribution that you will have. And that uniform distribution results in F divided by A as the average stress. That is what is the actual stress or at all points on that particular cross section that we are dealing with. So now we are walking through from the load, that is the first column, to the second column, and that's where we have introduced the so-called equilibrium equation. Okay. In reality, the equilibrium equation should depend only on natural laws. And in this case, the natural law that we are talking about is the reciprocity, equation of reciprocity, or law of reciprocity, of which Newton's third law is a classic way of stating it. So the action that is there is the force, because that's what we are giving as the input. The output is something coming from the structure, which is trying to react to that input that we have given, and it is trying to react to it through the stress that is coming out, and which is what is your sigma 1,1. So now what Newton's third law says is every action has an equal and opposite reaction. So truly speaking, I should just say F1 equal to sigma 1,1. But in this case, I'm talking of two different kinds of quantities. One is a force, which has the unit newtons. The other is a stress, which has the units Newton per meter squared. So they are dimensionally different quantities. Because we are dealing with dimensionally different quantities over here, that's why the A comes in. Actually speaking, A is a geometric factor. Area of a cross section is something related to the geometry of the cross section, right? Or sizing of the cross section. Truly speaking, it should not be part of any natural law or equilibrium equation, etc. All aspects of geometry should come out, as we remember, is between the strain deformation. So that's where the geometry makes an impact. Whereas here it's the material which makes the impact between the stress and the strain, and we get what is known as the constitutive law. And here we get what is known as the kinematics, right? But you see that an A has appeared here. It is just a strange thing that we have to deal with, because we are dealing with two different dimensionalities. One is a force dimensionality, the other is a force per unit area dimensionality. And to take care of that, that area is coming into the picture in the equation. So it's kind of superfluous. But what is governing it, remember, is a natural law. And that natural law in this case is the natural law of reciprocity, one of the most fundamental natural laws that you can ever have in any field, not only mechanics, but if you're looking at other branches of physics like electromagnetics or photonics, etc., optics, which is what I meant. All of those, you will see that this law of reciprocity works at various length scales, time scales, etc. And therefore, this is something of great importance to remember. If you're dealing with the same dimensionality quantity, this is just a question of equating them. But since we are dealing with two different dimensionalities, we have to bring in the area over there. But essentially, what it's saying is that the reaction and the action expressed in the same dimension are counteracting each other to keep the free body diagram, whatever we see at the bottom of the slide over here, is essentially maintained. So in this case, static equilibrium, but it could be both F1 and sigma 1,1 could be functions of time as well, in which case it's a dynamic equilibrium. At different instants of time, they are of different values, but the product of sigma 1,1 into A continues to match F1, so that it's essentially a dynamic equilibrium that is taking place. So now we have been able to move one step. We have started with a known quantity, which is your F1. So we started with this, which is a known quantity. And we have got the first unknown, which is your sigma 1,1, because of this equation that we had, which is the equilibrium equation. Okay, so we have made one step forward towards the solution. Our primary goal is to determine the U1. That is what is the primary thing, because in reality, what you actually perceive through your sense organs, especially your sight, is the force that is applied and the displacement that results out of it, sometimes rotation, but essentially deformation. Whereas these quantities of stresses and strains are intermediate quantities which are introduced to go in a step-by-step approach in order to get to what you want, in a very systematic way, so that even in more complicated problems, you will not falter. That is the whole idea. But we are starting with a simple example so that we understand these steps very clearly. So our next step, the second step that we want, is to go from what is now known, because we have introduced the equilibrium equation. So in the presence of this, it becomes a known. So now we want to get to the second unknown quantity, which is the strain gamma 11, okay, which is a normal strain in the x1 direction. So if you want to do that, we have to correlate what we already know. We know F1, we know sigma 11. In terms of those quantities, or at least one of those, we want to get gamma 11. So what is that equation? That is your material constitutive law. Can you explicitly state that for me? What is the relation between sigma 11 and gamma 11?
Can you do 1 over the Young's modulus times just sigma
Absolutely, yeah.
1?
Right. So 1 over the Young's modulus times your sigma 11 should be equal to your gamma 11, because that is the constitutive law that we have been dealing with. But are there any assumptions involved in this whole thing?
I think in this case, we're assuming that it's planes. We're using the in-plane assumption where there's no stresses coming in the other two directions. That's one
That's
thing.
correct. That's correct. If you had either of these stresses, then you would have a gamma 11 coming because of them as well, because there's a Poisson's effect. Here only gamma 11 is dictated only by sigma 11, which means that we have to ensure that sigma 22 and sigma 33 are 0, which is very easy to do, because I just have to put this specimen in a UTM. I pull it apart. I measure these forces using the load cell. I have a strain gauge which measures my gamma 11. I can easily correlate those two and therefore validate this particular model. And why is this valid? Because these surfaces on the left and the right edge, and the edge which is towards you and towards me, all of these are free edges. When you have a free edge, the boundary condition is that there is no stress, and therefore there is no sigma 22, there is no sigma 33. Sigma 22 equal to 0, sigma 33 equal to 0. Sigma 11 is the only stress that we are applying, because we are applying F1, and F1 divided by the cross-sectional area, because it's a prismatic structure that we have taken. So in a prismatic structure, it just becomes F by A, and the area of cross-section that we have, even if it's non-prismatic and it is tapered, at that location at which we are interested in the stress, we have to take that area. That area will be varying, of course, along the length of the rod. But in this is a simple example, we have taken the constant cross-sectional area throughout. It's a prismatic beam, and therefore it is just F1 equal to sigma times sigma 11 times A. And now to the second step, we have got your gamma 11 as 1 by E times sigma 11. If it were a composite, then we would have to put a subscript for the E and take it as EL. Okay, but here we are dealing with an isotropic material, which is why 1 by E is valid. So that is the other assumption that we are making over here, that it's an isotropic material, and therefore there are no couplings with shear strain. I don't need to use a subscript for E. So there are many simplifications which come because of that, right? So now we have made one more step towards our quantity of interest, U1. We have started from F1, which was given to us. We didn't have sigma 11. We used the natural law, which is Newton's third law, equilibrating a particular free body diagram. And then we got to sigma 11. And then we used material property, which is the constitutive law, got from sigma 11 to gamma 11 by dividing sigma 11 by E. We got to gamma 11, which is the main strain that is there. As Nafis already mentioned, we have gamma 22 and gamma 33 as well, just that we are not talking about it right now to keep things simple. But if we want, we can determine those as well, because we know the Poisson's ratio in those directions. If it's an isotropic material, then it's the same Poisson's ratio in all directions. We can get that as well. But now that we have gamma 1, can we get U1? What is the equation there? We have already written that it should depend on the geometry, and it's called kinematics. But what is the specific equation that relates gamma 1 to U1?
Well, we know that the strain in the 1 direction will be the derivative of the displacement with respect to the x1 direction. So if we want to get, so can we do like the reverse of that? So can we integrate in order to get displacement?
Absolutely, absolutely. So your gamma 1 in a linear strain problem is just given by U1 comma 1. Okay. In reality, of course, you will have quadratic terms, etc., because that is very, very critical for flight vehicle structures where the displacements and rotations are very large. Because the displacements and rotations are large, you cannot deal with just this linear strain displacement relationship, which is valid only when the deformations are small. Okay, so just keep this at the back of your mind, but we don't want to complicate the situation. We want to keep things simple, just to understand this flow of information from the unknown to the final, from the known to the final unknown, with what we want to determine. That's why we are keeping everything in the simplest possible way. Okay, so an assumption that is involved over here is geometric linearity, which actually is a wrong assumption to make. It's not the right assumption, but just that we want to keep things simple. So therefore, we are going with that. So as Nafi said, now we have no gamma 1, and we want to determine U1. So we have to integrate this. And of course, when you integrate, you end up with a general solution. So then you have to apply the boundary condition. We know a boundary condition over here that U1 equal to 0 at x1 equal to 0. So therefore, we can solve for that undetermined or unknown coefficient that will result when you integrate that. Because U1, if you integrate for a constant gamma 1, you will just get that gamma 1 naught times x1 plus let me just call it C1 x1 plus C2 x2, which is what you will have when you integrate that for a constant. And that constant, of course, is given by your sigma 1 by E, which in turn is given because you can back substitute all these values, and the governing equation that you had will be, of course, EA times dou U1 by dou X1, or I can just write it as U1 comma 1 I did earlier, and that's your F1. Okay, so this is the equation that we have, and if F1 and EA are constants, then obviously you get U1 is equal to F1 by EA times x1, which is the integration, and then a constant C1, which goes to 0 because of this particular boundary condition that we had, which said that U1 equal to 0 at x1 equal to 0. So that will be possible only if C1 equal to 0. If C1 is anything else, that will become the value of U1 at that location, which is actually quite useful for actual flying vehicle structures, because you will not have a zero displacement, but this is a part of a vehicle, which is a flying vehicle. It could be a wing, let us say. So it's moving with the aircraft. So you will have a certain displacement field which is associated with the dynamics of the aircraft itself, and therefore you will correlate with that. Okay. Now we are breaking apart that problem, and we're talking of a aircraft fixed reference frame with respect to this U1, U2, U3 that we are using on this page are defined, and therefore we can say U1 equal to 0 at x1 equal to 0, and therefore solve for that. So now you understand this whole process of going from a known quantity F1 to an unknown quantity U1 that you wanted to determine in terms of the variables which come up And those variables, very interestingly, involve, of course, the load over here, which was the input, which is the causative factor, which is because of which that the output is happening, which is your displacement. So now that is dependent on two quantities because of two sets of equations that we used in between. One is the material property, and the other is a geometric property. And this is something that will always happen, and which is why I've been stressing right from the beginning that structural analysis or structural design, for that matter, anything related to structures, has two important aspects to it. One is the material, the other is the geometry. So all your final equations between the load and the deformation will include both of those. Why? Because the two sets of equations that we are dealing with, material and the geometry, are essentially bringing that apart. Now, here in this particular case, and in many simple cases, you will see that geometry, instead of coming from the kinematics, seems to be coming from the equilibrium equations, as it did in this case, the area. But I already clarified that for you, that the only reason it's appearing there is because we are dealing with apples and oranges on either side of the equilibrium equation. One has a dimension of force, the other has the dimension of force per unit area, and therefore to correlate that, we have to bring in the area over there. Otherwise, in the natural law itself, the geometry didn't have a role to play. It should usually have it from the strain deformation relationship. So is this whole example very clear? It's a very trivial and simple, even silly sounding example, but the whole idea is to bring you up to speed with this bucketing into four categories: load, stress, strain, and deformation as far as variables are concerned, and bucketing into three categories as far as equations are concerned, namely your the equilibrium equations, the constitutive law, and the kinematics. Is this example clear, so that we can get on to a more complicated problem in the afternoon session? If there are any questions, I'll be happy to answer.
I don't think we have any questions, so we're good.
Okay, great. So go ahead for lunch. We'll start at 2 once again, if that's okay with you. Yeah. Okay, see you at 2 then.